and welcome to this tutorial on data management for AIOps Part 2. In this session, we'll explore essential concepts that shape how data is processed, structured, and utilized. We'll begin with data preprocessing and feature engineering, where you'll learn how raw data is cleaned and transformed to improve model performance. Next, we'll dive into the importance of labeling and tagging data, a crucial step in ensuring accurate predictions and insights. Finally, we'll break down real-time versus historical data, helping you understand when to use live data streams versus past records. Whether you're a beginner or looking to refine your skills, this tutorial will give you the foundational knowledge to work with data effectively. Let's get started. We shall begin with data preprocessing. Data preprocessing is the first step in preparing raw data for analysis. Imagine getting vegetables fresh from a farm. Before you cook, you have to wash them, chop them, and remove anything unusable. That's essentially what data preprocessing does for data. It cleans and organizes it. Let's understand why data preprocessing is important. Raw data is rarely perfect. It might have missing values, image a survey where some people skipped a question. Inconsistent formats, one column might use yes and no, while another uses true and false. Outliers, data points that are unusually high or low and could skew results. If you don't preprocess your data, any analysis or machine learning model built on it will likely produce poor or misleading results. Let's break down the steps involved in data preprocessing. 1. Data cleaning. This is like giving your data a bath. It involves removing errors and inconsistencies. 2. Data transformation. This step ensures data is consistent and in a usable format by standardizing and encoding data. 3. Data reduction. This simplifies the dataset by removing irrelevant features. 4. Data splitting. If you're training a machine learning model, you'll divide your data for model training. Once your data is clean and preprocessed, the next step is feature engineering. Feature engineering is the process of creating new features, or variables, that make your data more meaningful and useful for analysis or modeling. Think of it as giving your data extra superpowers to make it more informative. So, why is feature engineering important? Features are the input variables a machine learning model uses to make predictions. Better features lead to better predictions. Imagine teaching a machine to predict whether a photo shows a dog or a cat. Features like fur texture and ear shape will be much more useful than, say, the image size, to predict if it is a dog or cat. Now, let's break down the steps involved in feature engineering. 1. Feature selection. This involves choosing the most relevant features from your dataset. For example, if you're analyzing student performance, features like study hours and attendance are more relevant than their favorite color. 2. Feature creation. Here, you generate new features from existing data. For example, creating an age column from a date of birth column. 3. Feature transformation. This modifies existing features to make them more useful. 4. Interaction features. These are features created by combining two or more existing ones. For example, if you're predicting car prices, combining engine size and mileage into a new feature called performance ratio might improve your model. 5. Feature scaling. This step ensures that all features are on a similar scale. For example, in a dataset with house prices in the millions and room counts in single digits, scaling ensures one feature doesn't dominate the analysis. While data preprocessing and feature engineering are powerful, they come with challenges. 1. Time-consuming. Cleaning and transforming data can take up to 80% of a data project's timeline. 2. Expertise required. Knowing which features to create or select requires domain knowledge. 3. Overfitting risk. Adding too many features can cause a model to learn patterns specific to the training data, making it perform poorly on new data. To overcome these challenges, it's important to test and validate your preprocessing and feature engineering steps thoroughly. Now, let's discuss about the importance of labeling and tagging data. Imagine trying to organize a giant library where none of the books have titles, authors, or categories. How would you find what you're looking for? How would you make sense of what's inside? This is what working with raw, unlabeled data feels like. It's chaotic and almost impossible to use effectively. That's where labeling and tagging data come in. Data labeling is the process of assigning meaningful information or categories to data. Think of it as adding a name tag or label to each piece of data so you can identify what it is. While data tagging is similar, but often involves assigning multiple descriptors or keywords to data to provide more context. Labeling and tagging data are crucial for several reasons. 1. Organizing data. Labeled and tagged data is easier to search, sort, and retrieve. 2. Powering machine learning models. Labels are the foundation of supervised learning, where models learn from labeled examples to make predictions. 3. Enabling personalization. Tagged data helps create personalized user experiences. 4. Improving searchability. Tags act as metadata, making data more searchable and easier to filter. 5. Supporting data analysis. Labels and tags make it easier to analyze trends, patterns, and behaviors within datasets. Now, let's understand the difference between real-time data and historical data because not all data is the same. Let's start with real-time data. Real-time data refers to information that is calculated, transformed, processed, analyzed, and used immediately after it is generated. It's all about speed and immediacy. Some characteristics of real-time data include timeliness. Real-time data is generated and processed instantly, often within milliseconds. Continuous flow. It arrives in a steady stream from various sources. Action-oriented. It's used for tasks that require immediate decisions or responses. Some examples of real-time data include stock market data. Stock prices fluctuate every second. Investors rely on real-time updates to make quick trading decisions. Weather monitoring. Sensors provide real-time data about temperature, wind speed, or rainfall to issue timely alerts during severe weather conditions. IT system monitoring. Tools like AIOps use real-time data to detect system anomalies, like a sudden spike in CPU usage, and take corrective actions immediately. Navigation apps. Apps like Google Maps use real-time data from GPS and traffic sensors to suggest the fastest route and provide live traffic updates. Real-time data is crucial when immediate actions are required. Example: detecting fraud in a credit card transaction. Situations are dynamic and constantly changing. Example: monitoring network traffic in IT systems. Customer experience depends on up-to-date information. Example: showing product availability on an e-commerce site. Now let's talk about historical data. Historical data refers to information that has been collected, stored, and analyzed over time. Unlike real-time data, it isn't processed immediately. Instead, it provides a long-term perspective. Some characteristics of historical data include stored information. Historical data is typically saved in databases or data warehouses. Retrospective analysis. It's used to look back at trends, patterns, and events. Larger time frame. Historical data spans days, months, or even years. Some examples of historical data include sales records. A business can analyze historical sales data to identify seasonal trends and plan for high demand periods. Website analytics. Tools like Google Analytics store historical data on website traffic to help marketers understand long-term user behavior. Climate research. Scientists use decades of historical weather data to study climate change and predict future patterns. Customer purchase history. Retailers use this data to identify loyal customers and recommend products based on past buying habits. Historical data is valuable when you're looking for trends and patterns over time. Example, analyzing user engagement on a social media platform. Making strategic decisions. Example, using past sales data to plan marketing campaigns. Conducting predictive analysis. Example, using past energy consumption to forecast future demand. As we wrap up this tutorial, let's take a moment to revisit the key concepts we covered. We started with data preprocessing and feature engineering, where we explored how raw data is cleaned, transformed, and optimized to improve the accuracy of models and decision-making. Proper preprocessing ensures data is structured, relevant, and ready for analysis. Next, we discussed the importance of labeling and tagging data, a crucial step that makes data more searchable, meaningful, and useful. Whether it's organizing datasets, enhancing machine learning models, or enabling personalized experiences, proper labeling and tagging help unlock the full potential of data. Finally, we examine real-time versus historical data and their unique roles. Real-time data is processed instantly, driving immediate decision-making, while historical data provides long-term insights by analyzing past trends. Both are essential for data-driven strategies in today's fast-paced digital world. By understanding these fundamental concepts, you're now better equipped to handle, analyze, and leverage data effectively. Before you go, take your learning to the next level. Click the link in the description to access this lesson inside the MotivaLogic Academy Learning Management System. There, you'll find a quiz for every lesson, hands-on labs, and real-world projects designed to test and strengthen your understanding. While you're there, explore our full catalog of advanced, hands-on courses and downloadable resources, all created to help you move from theory to real-world expertise faster. Don't forget to like, subscribe, and share. And turn on notifications so you never miss a future lesson. Thank you for watching.